Okay, picture this. It's 1971, you're at an airport, and you see a couple of guys carefully loading these big, heavy suitcases onto a regular commercial flight. But here's the thing, they're not filled with clothes. Inside those cases are some of the most precise instruments on Earth, and they're on a mission to answer a question that would completely change how we see reality itself.
So, the men you're looking at here are physicists Joseph Haefel and Richard Keating. And no, they weren't going on vacation. They were about to kick off one of the most brilliant and important experiments of the 20th century. And the goal? To see if time itself could be bent, stretched, and squeezed just by flying around the world.
You see, they were putting a really wild idea to the test, an idea proposed decades earlier by none other than Albert Einstein. And it's a concept that pretty much shatters our everyday intuition about how the world works.
For Einstein, time wasn't some universal clock ticking away at the same pace for everyone everywhere. No, he argued that the passage of time is relative. It actually depends on how you're moving and where you are in a gravitational field. And what that means is that your personal clock could literally be running at a different speed than someone else's.
This slide breaks down the two mind-bending effects that Haefel and Keating were looking for. The first one, from special relativity, is called kinematic time dilation. Basically, the faster you move, the slower time passes for you. The second one, from general relativity, is gravitational time dilation. The stronger the gravity, the slower your clock ticks. This means time literally runs a tiny bit faster at the top of a mountain than it does at sea level. It's wild.
So the key takeaway here is this. Time dilation isn't just a feeling or some kind of perception. It is a real, physical phenomenon. A clock that's actually moving, or one that's deep in a gravity well, will physically tick slower than a stationary clock that's far away from that gravity.
Probably the most famous thought experiment to explain this is the twin paradox. So, you've got two twins. One of them blasts off into space, travels near the speed of light, and then comes back. For her, maybe only a few years have passed. But back on Earth, decades have gone by. She returns to find her twin is now an old man. It's not a true paradox, it's the astronaut twin who experiences acceleration and changes their frame of reference, but it does an amazing job of showing just how weird the consequences of relativity really are.
But you know, a thought experiment is one thing. Haefel and Keating wanted to prove it for real, so they designed an experiment that would take them and their clocks all the way around the world.
They couldn't exactly use a spaceship, but they could use commercial jets. And they couldn't just use a regular wristwatch, they needed something incredibly precise. So they used 4 cesium atomic clocks, which keep time by tracking the vibration of cesium atoms. We're talking over 9 billion ticks every single second. These were the most accurate clocks man had ever built.
The design of the experiment was just brilliant. First, they synchronized all their clocks perfectly. Then, they flew one set eastward. Flying with the Earth's rotation meant this clock was moving faster relative to the Earth's center. The other set flew westward, against the rotation, moving slower. All the while, a reference clock stayed put on the ground. The final step was just to bring them all back together and see if their time still matched up.
So, after flying tens of thousands of miles, they brought the clocks back to the lab, and what they found would confirm one of the wildest predictions in the history of science. The results were just staggering. Look at these numbers. The clocks that flew eastward, the faster ones, actually lost 59 billionths of a second compared to the clock on the ground. Meanwhile, the clocks that flew westward, the slower ones, gained 273 billionths of a second. And the most incredible part? These numbers matched Einstein's predictions almost perfectly.
This was the smoking gun. It was definitive proof time is not absolute. Literally flying around the world had caused these clocks to experience a different amount of time than the one that stayed home. The implications were just enormous.
Okay, so a few billionths of a second. It's a great scientific result, but does it really matter? I mean, who cares about such a tiny sliver of time? Well, it turns out you do every single day.
The technology that powers the maps on your phone, the Global Positioning System, or GPS, would be completely useless without correcting for these very relativistic effects.
So here's why. GPS satellites are moving incredibly fast, which, according to special relativity, slows their clocks down by about 7,000 nanoseconds a day. But they're also way up high above the Earth in weaker gravity, which, according to general relativity, speeds their clocks up by 45,000 nanoseconds a day. The net effect is that every single GPS satellite clock gets ahead of clocks on Earth by about 38,000 nanoseconds every day.
And if we didn't correct for that tiny difference, well, the positioning error would add up to about 10 kilometers every single day. Your GPS would tell you your house is in the next town over. Relativity isn't just a theory, it's a vital piece of modern engineering.
So it has these profound practical effects, but the philosophical implications are even more mind-boggling. If time isn't universal, what does that say about the nature of reality itself?
Einstein's former professor, Hermann Minkowski, realized that if time is relative, it can't be separated from the three dimensions of space. They are woven together into a single four-dimensional fabric he called spacetime.
And this leads to this astonishing idea called the block universe. This theory suggests that all of time, every moment that has ever happened and every moment that ever will, already exists. The past, present, and future are just different locations in this 4D block of space-time. Our feeling that time is flowing is just our consciousness moving through it.
This idea challenges our most basic experience of reality. It suggests that tomorrow is just as real as today. The future isn't something that's going to happen, it's a place that's already there.
So, from an experiment with clocks on a plane, we arrive at this deeply unsettling question. If the block universe theory is right, if all of time is laid out like a landscape, then what makes this particular moment now so special? Is it special at all? Or is it just the place where we happen to be?